Hello everyone, welcome to week 17 section of your calculus class. During this week, we'll learn about the fundamental theorem of calculus, which is in chapter 6, section 4 of your textbook. You can find it on page 298 until page 309. The objectives of the lesson are to use the fundamental theorem of calculus, part 1 and part 2, and also to use integration in finding areas of a region between a function and the x-axis, or areas of the region between two specific functions. Here is the statement of the fundamental theorem of calculus, part 1. If f is continuous on the interval a comma b, then the function capital F of x is equal to the integral of f of t dt from a to x, where a is any constant and x is the variable of the function, the derivative at every point x in the interval a comma b, and d of capital F by dx is equal to d by dx of the integral f of t dt from a to x, which is exactly equal to f of x. In other words, this means the definite integral of a continuous function is a differentiable function of its upper limit of integration. Or putting it more precisely, the fundamental theorem of calculus part 1 can be stated as follows. The derivative of an integral of a function integrated from a to x is exactly the same as f of x, which means the derivative of an integral of a function is the function itself. Okay, so this tells us that the process of integration and the differentiation are inverse process of each other. Let's see the first example of our lesson. Evaluate each of the following integrals using the fundamental theorem of calculus part 1. The derivative of the integral of cos t dt from negative pi to x is equal to how much? We say that the derivative of an integral is the function itself. We only need to replace the upper limit of integration x by t, and then our answer is cosine of x. Look at the second one. The derivative of an integral of 1 over 1 plus t squared dt, where you integrate from 0 to x. Look at the upper limit of integration, it's x. You only need to replace the variable t with x, and the derivative of the integral is 1 over 1 plus x squared. Let's see the second example of the fundamental theorem of calculus. Find dy by dx if y is equal to the integral of cos t dt integrated from 1 to x squared. As you can see, the upper limit of the integration is not x, it's x squared. That means y is the composite of the two functions, the integral from 1 to u of cos t dt, where u is equal to x squared. So applying the chain rule to find dy by dx, we have dy by dx is equal to dy by du times du by dx. The symbol that appears as a box here is multiplication. I hope you remember the chain rule. Dy by dx is dy by du times du by dx. The y is given in the expression, the integral from 1 to u of cos t dt. So you can replace that one and rewrite d by du of the integral of cos t dt times du by dx. Since u is equal to x squared, du by dx is equal to 2x, and the integral of the integral of cos t dt from 1 to u is cosine of x squared, or cosine of u, and the du by dx is x squared. That makes your final answer 2x times cosine of x squared. Okay. In the third example, we are asked to find the derivative of the function y is equal to the integral from x to 5 of 3t sine t dt. As you can see from this integral, the order of the limit of integration is in such a way that the variable is in the lower limit and the constant 5 in the upper limit. But in the statement of the fundamental theorem of calculus part 1, the constant should be in the lower limit and the variable should be in the upper limit. So to rectify this one, we have to change the order of limit of integration and introduce a negative sign in front of the integral. Hence, the derivative of the given integral is equal to d by dx of negative. We introduce the negative sign and revert the order of the limit of integration from x to 5 to 5 to x, and then 3t sine t dt. The negative sign can be factored out, and we are familiar with the derivative of an integral of a function is the function itself. So ignore the constant and replace x, replace t by x. That makes your answer is equal to negative 3x sine x. Let's continue with the fourth example of the lesson. Find the derivative of the function y equal to the integral of e to the power of t dt integrated from the lower limit to x to the upper limit x squared. Here you can see that the lower and upper limits of integration are both variables. They are not constants. The lower limit is 2x and the upper limit is x squared. So we'll be forced to break into two integrals where we can take an arbitrarily constant number so that we can integrate from 2x to 0 and then from 0 to x squared and take the sum of the two integrals. Okay, this is what it means. D by dx of e to the power of t dt from 2x to x squared is the same as d by dx of the integral from 2x to 0 of e to the power of t dt plus from 0 to x squared of e to the power of t dt. But the integral from 2x to 0 should be reversed and written. I mean, reverting the limits of integration from 2x to 0 to 0 to 2x, but this time we have to introduce a negative sign. That's why we used the minus sign, because 2x was at the bottom, I mean, and the lower limit of integration, 0 was in the upper limit of integration. We reversed them and introduced a negative sign. Now we have to apply the chain rule and differentiate the integrals. So the derivative of the integral of e to the power of t dt from 0 to x squared is done by replacing x squared in place of t. That gives you e to the power of x squared, but by chain rule we have to differentiate x squared. And similarly, in the second integral, the derivative of e to the power of t dt from 0 to 2x can be done by replacing 2x in place of t. That changes e to the power of t into e to the power of 2x, and we have to apply the chain rule in differentiating 2x. That gives us e to the power of x squared, and the derivative of x squared is 2x. That multiplies to give you 2x times e to the power of x squared in the last step, minus the derivative of 2x is equal to 2. 2 times e to the power of 2x is just 2e to the power of 2x. The fundamental theorem of calculus has got two parts. We have already seen the first part. Now we will see the second part of the theorem, which is stated as follows. If small f is a continuous function at every point of the interval in a to b, and capital F is its antiderivative of the same interval, then the integral of small f of x dx from a to b is equal to capital F of b minus f of a, which means if a capital F is the antiderivative of small f, then the integral is a numeric value which is calculated at the difference of f of b minus f of a, where capital F is the antiderivative of small f. This one is also another very powerful theorem of calculus. Let's do some examples to help us understand the second part of the fundamental theorem of calculus. Example 5. Evaluate the given integral using antiderivatives. Integrate x cubed plus 1 dx from -1 to 3. We are integrating a polynomial function, which we are very well familiar with. The integral of x cubed plus 1 is x to the power of 4 divided by 4 plus x. And we have to integrate this one from -1 to 3. If the antiderivative is x to the power of 4 over 4 plus x, we have to evaluate that from -1 to 3. That can be done by plugging in 3 in place of x first and find the value. Next, plug in -1 and find the value, and eventually find the difference between the two, which is 24. Okay, now let's see another example to help us understand the second part of the fundamental theorem of calculus. Evaluate the given integral using antiderivative. We are integrating a power function x to the power of 3 over 2. And I hope you remember the formula for integrating power functions. The integral of x to the power of 3 over 2 is 2 over 5 times x to the power of 5 over 2. This can be obtained as x to the power of 3 over 2 plus 1 divided by 3 over 2 plus 1. And the antiderivative is 2 over 5 times x to the power of 5 over 2. But this should be evaluated from 0 to 5. Plug in 5 first, and then plug in 0, and find the difference. And the ultimate outcome is 22.361. Example 7. Evaluate the integral using antiderivatives. Evaluate the integral from 0 to pi of 1 plus cos x dx. If our variable of integration is x, then the integral of 1 is equal to x, and the integral of cos x, or the antiderivative of cos x, is sin x. But x plus sin x has to be evaluated or integrated from 0 to pi, which can be obtained by plugging in pi first, which gives you pi plus sin pi, and obviously sin pi is 0. And again, plug in 0 in the expression. 0 plus sin 0 is 0 in aggregate. So you will have pi, which is 3.142 as the integral of the given function. Example 8. Evaluate the integral of 1 minus root u over root u du from 0 to 4. In order to integrate the given expression, we can share the denominator root u into 1 over root u minus root u over root u. 1 over root u is obviously the same as u to the power of minus half. Root u over root u is 1. Next, we need to integrate. The integral of u to the power of minus half can be obtained by u to the power of minus 1 over 2 plus 1 divided by the same expression minus 1 over 2 plus 1. And that gives you 2 times u to the power of half. And next, the integral of negative 1 is u itself, because the variable of integration is u. Now we have 2u to the power of half minus u, or indirectly we can say 2 times the square root of u minus u. But this must be integrated from 0 to 4. That means we have to plug in 4 in place of u first and get the value. Next, we have to plug in 0 in the same expression to u to the power of half minus u and get another value. Then we have to find the difference between the two. And 2 times root 4 is the same as 2 times 2, 4. 4 minus 4 is 0, and 0 minus 0 is 0. So the integral is 0.